Honors Trig Pre-Calc. We're going to do section 1.2 today, functions and their properties. I'm going to preface this by saying this video might be a little longer than the last ones, but I think you'll be okay. So we're going to start by asking the question, what is a function? A function is something that assigns all elements of a domain to a unique, or I guess an unique, I don't know, a unique element in the range. Sometimes I've seen a function described as like a machine. This is a weird picture, I promise, where you are plugging in some value, x, right? That's a part of the domain. And the function does something, changes it in some way, and you get out a y value, otherwise a range. We also often call x's domains the independent variable, y being the dependent variable, sometimes input and output. And how do we denote functions? This is the most important thing. Y is equal to f of x. That's how we read that. Y is a function of x, we could say. Y is a function of x. How do we know if something is a function? Well, we said, remember, that elements in the domain are paired with one and only one element in the range. So we cannot have two y values for one x value. One way to check if something is a function visually is called the vertical line test, which does hopefully what you would think. You take a vertical line. So if a vertical line hits a graph more than once, that graph is not a function. We'll do more examples, obviously, in class, but I do want to show you just one example. If this is my graph and I draw a vertical line down, it hits that graph in two different places. This is not a function. Cannot have two different y values. Here's one y value, here's the second y value for the same x value. All right, domain. We mentioned this earlier. It is all x values that make the function true. That make f of x true. If we are talking algebraically, oops, that's supposed to be an L. Algebraically, there are two big things that we need to look out for. The first is fractions, because we cannot divide by 0. Right? That is a big math sin. You never want to divide by 0. And the other thing we have to look out for is square roots. While we can take the square root of 0, we cannot take the square root of a negative number. You cannot have a negative under the square root. Now, of course, that is something that we can do, right? We just talked about the square root of -3. We could say that's the square root of 3i. It's just an imaginary number, and for functions, we are really looking at real numbers. Range is our y values. And realistically, the easiest way to think about range is by just visually seeing the graph. What y values does it have? But if you are not given a graph, to figure out the range, you really just want to consider what y values your domain will produce. And of course, we will do examples of all of these in class. The next thing we get to talk about is continuity. Continuity is meaning, is the function continuous? To be continuous means that there are no breaks in the function. So this is a very visual idea. I have a bunch of graphs here. I'll just kind of point some out. This first function is continuous for all x. There are no breaks, there are no holes, there's nothing weird going on here. In the second one, you notice that there is something called a hole, which is literally a hole in the graph. It is also known as a removable discontinuity. For this third function, it's a similar one, a removable discontinuity. The difference, though, between, let's say this is A and B, if you notice, in A, there is a point on the graph at that x value. It's just not filling that same space in the function. Then we've got our next example, a jump discontinuity, which does what it says. The graph literally jumps up. And last but not least, we have an infinite discontinuity, where we have something called a vertical asymptote, which we will talk more about in a moment. If you need to pause the video to continue sketching these, by all means do so. Otherwise, we are going to talk about increasing and decreasing. Increasing and decreasing is referring to essentially the slope of the function. If a function is increasing, that means it is rising from left to right. Left to right. Or it has a positive slope. To be decreasing would obviously mean the opposite, that it is falling as we move from left to right. Or another way to think about it is that it has a negative slope. So like with the last example, I'm going to show you some pictures of some functions. We'll consider these two first. Oops. This first one, we notice as I move from left to right, oh, that was kind of bad, I am rising. So this is an increasing function. Over here, as I move from left to right, I am falling. This is a decreasing function. Sorry, my pen is not doing great right now. We have two more visuals. In this third function, notice that it's not increasing or decreasing. We would say that this is constant. And in our last example, this function has a part that's decreasing, a part that's increasing, and a part that is constant. So functions don't need to be just one. They can have little bits and pieces from each of them. The next idea is boundedness, what it means to have a lower bound or an upper bound. It hopefully isn't super shocking, but if a function has a lower bound, that means it has some y value for which the entire function lies above. So I'll show you an example of a lower bounded function. Right here, this function has a lower bound, a y value. This is a y value that the entire function is above. Similarly, if I want to consider the upper bound of a function, that would be a y value for which the entire function lies below. So if we look over here, this function right here has an upper bound where the entire function is below this y value. And then to be bounded, means it has both an upper and a lower bound. So this function right here has a lower bound and an upper bound. And then if we look at this first example, notice this function continues on forever and ever in both directions. It does not have a lower or an upper bound. Local extrema is talking about minimums and maximums. So a local minimum is a value f of c for which every value in the range of f of x in the range of the function is is greater than f of c. I'm going to draw you a quick picture. So if I've got some function, let's say it looks like that. Here we have a local minimum where if I focus just from like here to here, let's say, this is the lowest point there. Local is really just focusing on a specific range of values. We could say the opposite is true, not opposite, but I guess a local maximum would also be the same thing, but it's just higher than every single value. And then there's something called a global minimum or maximum. So I'll go with a global minimum here would be something like this point, where it is absolutely the lowest point on the graph. Notice I just mentioned minimums here, but local extrema refers to both minimums and maximums. I'm just not going to write the exact same thing for local maximum here, if that's okay with you. Next, we got symmetry. This is something symmetric? So if something is symmetric to the x-axis, meaning it looks the same on both sides of the x-axis, this thing is not a function. So we actually don't have symmetry with respect to the x-axis. However, we do have symmetry with respect to the y-axis. That would be a function maybe that looks like this. Symmetric means, again, exactly the same on each side. If it is symmetric to the y-axis, we call that function an even function. And a really important characteristic with an even function is that if you plug in the opposite of x, it's going to be the same as plugging in just that positive x. Visually, here's some x value. I get this y value. Even if I plug in the opposite of that value, I am still getting that same y value. Another type of symmetry is symmetry with respect to the origin. One graph might look like this. So with symmetric to the origin, we are basically flipping it twice, and I'll try and go through this in class again because it's kind of hard for me to show you without my hands. But if it's symmetric with respect to the origin, we call it an odd function. And when I plug in the opposite of a value x, I get a complete opposite y value. So if I look at this, here's some x, and it pairs up with this y value, f of x. And if I plug in the opposite x value, I am getting the opposite y value, even in odd functions. Horizontal and vertical asymptotes. This is something we're going to do a lot with later, but for right now, we're just going to talk about asymptotes as basically a line, even though it's not officially a line, that our function is approaching. So if we consider horizontal asymptotes, I'm going to say it is a line y equals b that our function approaches as x approaches or gets close to positive or negative infinity. So I'll draw a quick picture. Let's say here is our asymptote. Again, y equals b. I say line because it doesn't actually exist. And maybe our function looks something like this, where it comes close to that and will continue getting close to that value. Something that our function approaches, the y values are getting close to this as x gets close to positive infinity. Note, you can cross a horizontal asymptote. Vertical asymptotes are a very similar idea. It's a line, again. It's not really a line, it's basically sometimes I think of it as like a magnet, and maybe I'll talk about that in class. A line, x equals a, that the x values approach as your y values approach positive and negative infinity. So I'll draw another picture. Let's say here's our asymptote, x equals some value a, and I could look maybe like that. As my y values are getting really, really big, they're going to positive infinity. My x values are getting close to this line. And last but not least, end behavior. This is telling us how a function acts as the x values approach positive or negative infinity. This means approach. And we're going to talk a lot about this one because this is something that actually has to do with limits, but we'll get there together soon. So I will see you guys on Monday or Tuesday. Have a great day.